when we talk about molecular bonding or chemical bonding, one of the most important theory is valence bond theory. So this theory is developed by Linus Pauling, where it integrates Lewis' proposal and Heither-London's theory to give rise to two additional key concepts in VBT. So according to Pauling's theory, a covalent bond is formed between two atoms by overlap of their half-wheel valence orbital, of which atom contains one unpaired electron. So what are the concepts of valence bond theory? It is used to explain the covalent bond formation in many molecules and the synthesis of early understanding of how covalent bonds are formed. So the key to this theory, or the output to this theory, is resonance and orbital hybridization. Okay, so what does it mean by orbital hybridization? It is when a bonding orbital share the characteristic of several types of orbitals, which will result a valence bond structure. So this valence bond structure, it is used when Lewis structure do not suffice to represent the different forms of coordination molecules that occur as a result of resonance. Okay. For example, in carbon dioxide, so each carbon atom has two unhybridized atomic p orbital and each oxygen has one available p orbital. Okay, if we look at this diagram here. But now, when the oxygen binds to the either side of the carbon, one of the p orbital on each oxygen forms a pi bond with one of the carbon p orbital, and sp hybridization occur, which lead to two double bonds. That's why we see that CO2 thus looks like this, and another one is another oxygen also double bond. Okay, this is pi bond, this is pi, while the other one is sigma. Okay, and this pi bond is result from the overlapping of p and p orbital. Okay, figure below illustrate how valence bond theory apply to the coordination compound, which is sulfur hexafluoride. So when we apply valence bond theory to a coordination compound, the original electron from the orbital of the transition metal is moved into non-hybridized d orbital, and the electrons donated by the ligand move into hybridized orbital of higher energy, which are then filled by electron pairs donated by the ligand. Okay, if we look at the example here, this is the arrangement of electron in S atom, just S atom, which is 1, 2, 3, 4, 5, and 6. Okay, and then we have SF6. So what happened? We have 6F here, 6F ligand. So what happened is that this 6 ligand donated 1 electron each, and then you need to add another 6. Okay, so in this case, this is 2, and then 2, and then 1 here. You know fluorine has 1 electron each because it is -1. So we need to have 6 fluorine electron from fluorine. Okay, 1, then one, then another one here, then another one here. So if we look at this orbital diagram, we can see that we have 1, 2, 3, 4, 5, 6 electrons coming from the 6 fluoride ion. Okay, and then we have another theory, which is the valence shell electron pair repulsion, or what we know as vsepr model. So vsepr model is used to predict the shape of the molecules and ion in which valence shell electron pairs are arranged above each atom so that the electron pair are kept as far away from one another as possible, which minimize the electron pair repulsion. So how are we going to predict the geometry of using vsepr model? So there are three general rules here. The first one, we determine from the electron dot formula of how many electron pair are around the center atom, and we count multiple bonds as one pair. And then we arrange the electron pair, and then the third one, we obtain the molecular geometry from the direction of bonding pairs. Okay, now when we look at this table, so the bond angle is 180, so the geometry is linear, and the electron domain, so electron domain consider those who are bonded and also the non-bonded. Okay, so if we have two electron domain here, two electron domain, so it is sp 1, 2. So it is sp without any lone pair. Okay, let's take a look at the bond angle of 120. So we will have a geometry of trigonal planar. In this case, we have 3 electron domain. 1, 2, and 3. So that's why it is sp2. 1s, 1p, and then another p. So we have 3 electron domain, 1, 2, 3. So in the case where you have one lone pair electron, so the geometry is bend. Okay, it is still sp2, but it is bend or V shape. Okay, next, when we have a tetrahedral geometry, the angle is 109.5 degree, and this is what we call as sp3 hybridization, because you have 4 electron domains here. You have 4 electron domains. So if there are no lone pair electron, it is tetrahedral. If there is one lone pair electron or non-bonding part, non-bonding electron domain, so you will get a trigonal pyramidal. And if you have two sets of lone pair electron, it becomes bend or V shape. Okay, let's take a look at trigonal bipyramidal geometry, where you have two types of angle here. So from this to this, from this to this, it is one. Okay, from this to this, it is 120 degree, and from this to this, it is 90 degree. So this is what we call as DSP3 hybridization, because you have 5 electron domain. So 5 electron domain is 1, 2, 1p, 2p, and 3p. So if there are no lone pair electron, it is trigonal bipyramidal. If you have one lone pair electron, it is a sawhorse or a seesaw. And if you have two lone pair electron, it is T-shaped. And if it has three lone pair electron, it becomes linear. Okay, now let's take a look at octahedral. So octahedral hybridization is D2sp3 because we have 6 electron domain. So 6 electron domain 1d, 2d, 1s, 1p, 2p, and 3p. So we have 1, 2, 3, 4, 5, 6 electron domain. So it is D2sp3. So if there is no lone pair electron, it is octahedral. So if you have one lone pair electron, it is square pyramid. And if you have two sets of lone pair electron, it becomes square planar. And if it has three lone pair electron pair, it becomes T-shaped. And if it has four lone pair electron, it becomes linear. Okay, that's the end of this video, and we will continue on the other topics in the next video.